Hi everyone. Today we're going to talk about thermal radiation. When you heat an object up till it's red hot or white hot, it's emitting electromagnetic radiation. And it's not hard to see why. The material's hot, the atoms inside of it are in random thermal motion, so that the positive and negative charges inside of the atoms are moving, and so they emit electromagnetic radiation. Okay? But interestingly, thermal radiation is very, very simple. And in fact, the theory of thermal radiation is one of the foundations of quantum mechanics. So let's go take a look. I'm going to show you some images now. 1 second. Okay, here's an image of molten glass in a furnace. This is an example of thermal radiation. See how it's orange hot? Something really interesting about this. The properties of the radiation only depend on the temperature of the furnace. They don't depend on what the furnace is made out of. Here you can see that. We're looking inside. Some of what we see is brick, some of it's the back of the furnace, and some of it is glass. But it all looks the same to us, even though it's all made out of very different materials. Okay. Now, the light that we see coming off of any of these objects includes both the light emitted by the object and the light that's reflecting off of it from other sources. So the simplest kind of object is a black object that doesn't reflect any light, and so all the light it emits is thermal radiation. And so we're going to focus on what are called black bodies. So these are absorbing objects that are emitting radiation because they've been heated up to the point that they glow. Okay? So I'd like to start by talking about some of the properties of black body radiation or thermal radiation. Okay, so one good example of a black body is a furnace or other object that's heated up to some temperature that has a hollow space inside. And then we drill a small hole to let radiation from this hollow space escape. Imagine this object being cold. If you look into the port here, into the hollow space, it will look completely black. But when we heat it up, it will be a source of radiation. So this is a typical implementation of a black body, a furnace with a hole in it so that radiation can escape. And what we're going to find is that the spectrum of the light that's emitted depends only on temperature. So if we take the radiation emitted by a black body and disperse it by breaking it up according to color, what we'll find is that the spectrum, the intensity as a function of wavelength, depends only on temperature. Here, I'll illustrate that. This is an experiment that we can set up in our labs. This is at Macalester College in room 146. Here's a furnace. Then light radiation is exiting this hole in the furnace, and some of it is being coupled into an infrared spectrometer. And then we can measure the intensity as a function of frequency with a spectrometer. Here we are. Here are spectra obtained for different temperatures. 300 degrees Celsius, 500 degrees Celsius, 750 degrees Celsius, 900 degrees Celsius. The basic shape looks the same for all of them, but they are different. And the reason they're different is because they're at different temperatures. Notice as we increase the temperature, the peak shifts to higher frequency, to higher photon energies. So at 900 it's here, 300 down here. In addition, the total amount of power, the area under the curve, grows very rapidly with increasing temperature. Okay? So these are some of the properties we'd like to talk about. First, I just would like to write them down for you and show you how these can be applied. Let's pause for a second and go to the notepad. There. Okay, so let's write down some of the basic experimental facts about thermal radiation or black body radiation. First, thermal emitters, black-body emitters, have an emission spectrum that's independent of material. We say that they have a universal spectrum. E as a function of F. And the shape of the spectrum is independent of material and it depends only on the temperature. This is interesting, right? If something is universal, it must be important. It must be tied to some deep property of the universe. And we'll see that that's right. The second rule concerns the total amount of power emitted by the black body emitter. Okay? The total emittance, which is the power per unit area emitted by, for example, the aperture here, by the hole, emitted by the black body, which means emitted out of that port, is given by a very simple expression. It's equal to a constant called the Stefan-Boltzmann's constant times the temperature to the fourth power. The temperature here is in Kelvin. And the Stefan-Boltzmann constant has the following value. It's the easiest constant to remember. It's 5.67 times 10 to the minus 8 watts per meter squared, Kelvin to the fourth. And so you can see that the emittance here, the total power emitted per unit area, has units of watts per meter squared. Okay? The third rule comes from the shape of this universal spectrum, and it tells us where the peak in the curve should be. Sorry. And it has a particularly simple form when it's written in terms of wavelength, which is what I'll do right now. So if we graph intensity versus wavelength, then the peak of the curve, the peak wavelength, is given by this. Lambda max is equal to a constant divided by the temperature in Kelvin. The constant has a name, Wien's constant, but I'm just going to write down the value, 2.898 times 10 to the minus 3 meters times kelvins, and then divided by the temperature, again in Kelvin. I won't make up a symbol for Wien's constant because it only appears ever in this one law, so we can just remember the number. So those are the most important properties of thermal radiation, at least for us. Here, let's use what we've learned so far to do a quick example. Consider the sun, okay? One looks at the light from the sun, it approximates a black body spectrum, and the peak of the spectrum occurs at a wavelength of about 500 nanometers, right in the middle of the visible spectrum. What a coincidence. Let's use this to estimate the temperature of the sun. So then the temperature of the sun should be 2.898 times 10 to the minus 3 divided by the peak wavelength, where we just solved the formula for here for temperature. And so taking a moment with the calculator to pump this out, we find that the temperature should be about 5,800 Kelvin. Pretty slick, right? Here, let's look at a second example concerning the sun. Now we know how hot it is. Of course, we know from astronomical observations how big it is. So that means we should be able to figure out the total power emitted by the sun. The total radiated power. Okay? So the power is going to be the area of the surface of the sun times the total emittance. So this, of course, is 4 pi r squared, the surface area of the sun, times Boltzmann's constant times temperature to the fourth. Okay? And then we can put in values. So the total surface area of the sun from its radius, which is about 7 times 10 to the 8th meters, this gives 6.16 times 10 to the 18 meters squared for the surface area of the sun. And then we're going to multiply by 5.67 times 10 to the minus 8, and then times the temperature to the fourth, 5,800 Kelvin to the power of 4. Okay? Straightforward. We just multiplied this. We found the surface area of the object. We know its temperature. And so we can use the Stefan-Boltzmann rule to figure out the emitted power. So putting this in, we can turn the crank and find a result. And the power we get is about 4 times 10 to the 26 watts. That's the power emitted by the sun, okay? It's a lot of power. In fact, if you use the Einstein's formula, E equals mc squared, this is equivalent to the mass energy of 4.4 times 10 to the 6 tons of material per second being converted into pure energy, okay? So just to give you an idea. All right, well, let's stop here for a moment.